Hello and welcome to Solutions Video 2. We're going to talk a little bit more about solutions and the way they behave. So far we talked about water, and it's critical to understand water because water is the main solute we'll talk about in chemistry. Of course, as you go forward in chemistry, there's other solutes to concern yourself with, but by and large, what we'll see in pre-AP and even in AP chemistry and most introductory college courses is water is your primary solvent. The terminology we use is important, so let's kind of get some things clear. If something is soluble, it can be dissolved. For example, we would say sugar is soluble in water. A solution is homogeneous if is a homogeneous mixture of two or more substances in a single phase. Now, by phase we mean the same thing we mean when we say what phase is this substance in? Solid, liquid, gas. So that would be like if you had substance that was all liquid in phase, okay? That could be an aqueous solution of a salt and water. It could be mercury with gallium mixed in. The dissolved particles are tiny. They're usually ions or small molecules. Dissolved does not mean ionized. This is very important when we talk about electrolytes. Solutions may exist as a solid, a liquid, or a gas. This is a table, and you might want to pause it and read for a moment. I just want to gloss over real quick what it is different types of solutions. And usually when we say single phase, it's not something you wouldn't notice more than one of the phases, so we'll be clear here. For example, something that's gas dissolved in a gas would be like oxygen and nitrogen in air. Now, there's very little molecular interaction here, so to call this solution is kind of a reach. Again, these are not lines that nature made up. These are lines that we drew. So sometimes they'll fit well, sometimes they won't. A gas dissolved in a liquid would be like oxygen dissolved in your blood. There's no clear bubbles of oxygen in your blood when it circulates through your body. But this is a true solution because the oxygen moves into such a small space that you don't notice a phase difference. Anything containing normal water will dissolve small amounts of gases from the air. Water is a great solvent for many reasons. And the oxygen that's around us gets dissolved in blood. There's rare occasions where a gas can be dissolved in a solid, like, for example, hydrogen dissolved into palladium. Palladium is actually used to store hydrogen in various applications. Obviously, a liquid dissolved in liquid would be like water dissolved in rubbing alcohol. Of course, keep in mind for a solution, whichever substance is in greater amount is the solvent, and what's in smaller amount would be the solute. A liquid-solid mixture would be like a mercury-gold amalgam or a gallium-aluminum alloy, where we have a liquid metal dissolved in a solid. A solid into liquid would be like glucose into water. Glucose is a molecule. It can be broken down almost to the molecular phase, or to the molecular state to be dissolved in water. Finally, a solid into a solid. Any alloy polymers are also solids dissolved in other solids. But again, the terminology for solute and solvent is kind of a reach here. So, we're sort of bending the rules in order to make this table clear. But these are true things. They're just not conventionally spoken about as solutions. A true solution is a homogeneous mixture in one phase consisting of at least two parts, solute and solvent. The solute is a substance being dissolved. It's usually in smallest amount. It's often a solid. The solvent is the dissolving medium. It's in the largest amount. It's usually a liquid. Water is known as the universal solvent. This little chart, salt and water make sodium chloride solution. An aqueous solution, a solid, liquid, or gas is dissolved in water. In this example, we have hydrochloric acid dissolved in water. The solute is hydrochloric acid. Hydrochloric acid comes to us in lots of different ways. It can come as a gas or an aqueous solution. And hydrochloric acid, and the solvent here is water. But what we see is when that hydrochloric acid hits water, it dissolves completely. We're wondering about why soon enough. It doesn't dissolve completely. It just doesn't just dissolve completely. It also ionizes completely. We'll talk about why very soon. Solvation is the action of the solute dissolving into a solvent until the solute is stable. When water is the solute, we call it hydration. Dissolution is similar but refers to the rate at which something dissolves. Now hydration is, if you look closely, these are all water molecules, the red with the white dash blue. And what you should notice is the orientation is different if the water surrounding a sodium cation or if the water surrounding a chloride anion. Notice the orientation has everything to do with the polarity we learned about in the bonding unit. The oxygen piece of water is very negative in charge, so it bears a lot of attraction to sodium, where the hydrogen groups are very positive, so they're very attracted to chloride. These are called hydration shells. It's a shell of water surrounding an ion that wouldn't otherwise be stable in water. A diagram of this reaction is not really a chemical reaction, more of a physical exchange. We have solid sodium chloride reacts with water to form aqueous sodium chloride in water. A lot to read here, so I want to kind of break it down. Keep in mind the intermolecular forces at play. They also exist between the particles in the solvent. The solute and solvent particles have an attraction for one another. When a solute is placed into a solvent, those particles completely surround the surface of that solute. Okay, imagine a grain of salt. If the attraction is greater than the solute-solute attractions are for each other, with the solvent-solvent, in this case water attraction for each other, the solvent particles will separate from each other, like the water molecules will pull apart from each other, and then pull the solute particles away from the solid and surround them, which forms a solvated solute, pulled apart solute. This is the solvation shell, okay, or the hydration shell. It's a three-step process, all right, and you have to take into consideration, are the forces at play greater or less than what I had? All right, sometimes that solute that you dropped into water won't dissolve, and that's because the force of attraction between the particles of solute is just too great. Anyway, this continues until the solute has reached saturation. In other words, no more can dissolve. At this point, an equilibrium condition exists. Equilibrium doesn't mean things stop. It means that things are no longer changing at any rate. They're still breaking down in formation of solute and solvent, but what you don't have is any change in that overall value. This is a GIF that's on the website, and I want you to take a look at it when you have some time. It's on the main page of the site. It's underneath the first video, and it just shows hydration shells forming. Okay, so check that out, please, on the website when you get a moment. Recall that electrolytes are aqueous solutions that contain substances that are able to conduct electricity. We researched this when we did our solubility and electrolyte lab in the bonding unit, so this should be reflective for you. It should make perfect sense that when we have dissolved ions in solution, we can expect a strong conduction of electricity and a strong measurable conductivity. Whereas if we drop a molecule like sugar in water, we don't get the same behavior. It's relatively non-electrolyte. It's a slightly more electrolyte than distilled water, but nothing significant. Keep in mind that ionic compounds that aren't soluble in water, and there are many, they can only act as electrolytes when they're molten. So there may be that possibility in a test question. Substances that ionize completely in water are strong electrolytes. Such examples are ionic salts, we're familiar with those, strong acids, and strong bases. Those things tend to be strong electrolytes. Substances that ionize partially in water are weak electrolytes. Weak acids and weak bases form weak electrolytes. Everything here about acids and bases we'll learn in the next unit, but for now these terms need to be part of your understanding. Finally, a little summary of solubility versus electrolyte behavior. And we first must ask ourselves, does the substance dissolve in water? If it does, then we ask ourselves, okay, does it conduct electricity? Okay, yes. If something is able to conduct electricity after it dissolves in water, it must be ionic. If something dissolves in water but doesn't conduct very well, we call it a polar covalent molecule. And if something doesn't dissolve in water at all, it's not going to conduct electricity. That's a nonpolar molecule. Um, a little bit further into the discussion about solubility, let's talk about how liquids become soluble in one another. The words we use to describe two liquids that are able to dissolve is miscible. This is the chemical formula and space-occupying drawing for isopropyl alcohol. Let's look at what we buy at the drugstore. At the drugstore, we buy isopropyl alcohol says 70% by volume. What you can't see here is that the other 30% is water. Okay? And when you pour this substance out of this container, you don't notice a phase difference. You notice one uniform system, and that makes this a nice homogeneous solution. That means that water and isopropyl alcohol are miscible. You'll notice water has this guy, this hydroxide on the end. This hydroxide is prone to hydrogen bonding, which makes water very happy. When we mix them together, you step back, you look at this, you say, oh, well, water and isopropyl alcohol tend to be pretty well mixed. That's miscibility. What's also interesting about different liquids being miscible in one another is they don't necessarily mix at a 1-to-1 volume ratio. It's pretty interesting. Because of the different ways these molecules can stack, when you put 100 mils of water with 100 mils of isopropyl rubbing alcohol, you don't end up with 200 mils of solution. You end up with about 186 mils of solution, which is just a testament to the fact that molecules stack differently when they're mixed together. Two liquids that are not able to dissolve into one another are immiscible liquids. And this is a diagram of the dividing line between where you would see water, which is more dense, and some fatty acid oil, which is less dense, on top of the water. We're going to get into solubility in the next video, but I want to introduce it before we start by saying the following. Solubility is defined as the number of particles that dissolve in a given quantity of solvent at a given temperature, producing a saturated solution. A saturated solution, you might remember from the POGL, contains a maximum amount of dissolved solute at a constant temperature. Now, when we work with these, we're usually going to use the standard of 100 grams of solvent, water, which is the same as 100 mils of water because the density of water is 1.00. So understand that what the definition of solubility is and what a saturated solution is, and we'll begin the third video for the solutions unit very soon. So thank you for listening. I hope you've taken some fantastic notes and are working your way through the practice packet. If you have questions, you need to come to class and ask them. Bring them to us the moment we get to class. Discuss it with the group, and that'll be all. I'll see you on the next video.